haven't been able to do as well as I would like is not just show you different ways of doing clustering, but actually show you how it gets done. And as you've been seeing, hopefully from the assignments, how clustering gets done is very different to take an algorithm, run an algorithm. There's lots of other details involved. So you can think of today as a kind of a case study. So Nitin is, as well as being the TA of this class, is also working with me on some clustering problems. And so what he's going to talk about today is sort of some of the actual issues that come up when actually doing clustering with actual data. And while you may not necessarily have take-home lessons or theorems or algorithms in this, I think you will probably relate to some of the things he's going through. You will understand that these are sort of common issues, and there are some general things we can tell you about how to deal with these issues. But there's not as much of a guiding principle or a formal statement of working. So having said that, I will let Nitin take over. On the show from here.
Okay.
You already have a question?
It's blur.
It's blur. Oh, it will get normal, I guess.
It's sort of flicking blur, not
blur.
So maybe you have to zoom out. That will help. So the agenda for today would be spectral techniques on coauthorship graphs. Basically, we'll pick a coauthorship graph, which is a very well-known graph for the people who research in graphs. So, and the next one that we'll look is the TSNE. I think most of you would have seen a TSNE in your second assignment. And then we'll look at why we have to normalize when it is good to normalize our data before clustering and when it is not. Okay, so let me begin with the coauthorship graph. So this, as I said, coauthorship graph is a graph which is very well known in the research area, and when people do research in graphs, they usually use this graph as a real world network. So, and this graph has nodes as the various researchers who have at least one publication, and an edge between different researchers is indicates if they have a co-authorship together. So basically, if let's say if there are two faculties and they have at least say 5 papers together, then we'll form an edge between those faculties, and we'll assign the weight of that edge as the number of papers that they have together. So and
is it just for the published?
I'm sorry?
Is it just for the published?
Yeah.
Not an archive?
No.
Just
Okay. Otherwise, we wouldn't.
Your turn will come, don't worry.
no.
Yes.
I'm curious to know. Okay.
Yeah. Otherwise, we wouldn't have any, means to know how. Yeah. So
Not an
from the
archive,
archive. Yeah. From the
But
archive.
frankly, there is no reason not to do it for the archive.
Yeah.
You could very well do it. I just said, I guess they haven't accumulated the data yet. But the
Right.
archive is an API, and you could easily imagine trolling the archive, getting the trawling through the archive, getting the data, and then hooking up, because they actually have HTML links for the authors. It's not just a name. So you actually have a unique, but so you could imagine doing this for the archive as well.
Actually, it is done for the archives.
It has for the archive?
Yeah, so Tamara Calder is coming next week, actually in a couple of her
Oh,
papers.
she's done this.
Yeah.
Ah, okay. So Tamara called us coming to give a talk at Ski,
Ah.
and sounds like she's done this for the archive as well.
Yeah, a lot of people, I guess, I don't know exactly.
So the graph has undirected edges. So from the graph itself,
Yes.
you cannot tell which people were together on a particular
It's
paper.
Yes.
You just know that they collaborated at some point.
Right.
At some point they were on a paper together.
Yeah.
Yeah, it's not a hypergraph. Yeah. So then all of you should definitely try to make it to her talk. It's going to be next Friday, right? This coming Friday or the next?
The next one right before the...
Right before spring break on Friday, 2 o'clock?
Well, spring break, the big 5. I think of it more like the big 5-day thing, that eating up spring break.
You must be a grad student. So yeah, so the basically Friday, 2 o'clock upstairs.
3 I think.
3 o'clock?
Because I think there was something at 1, and then there's a break.
Okay, so 3 o'clock upstairs in the ski room. Okay, good. This is good to know. Thanks. Yeah. So there you go. So that answers your question.
Yeah. So there are various versions of this co-authorship graph. Like people constructed different way, and we constructed this co-authorship graph that we use for our research from the ground. So where we started was there is a spreadsheet from the Brown's website, University's Brown, and which has a list of 2,200 faculties, and it has the corresponding research area. So what we wanted to do was pick those faculties from the sheet and
So
label.
wait, how was this data collected?
How's this?
The Brown data.
Oh, the Brown data. Okay, so Brown data was collected. I think 30 or so PhD students and master's students. They worked together to manually create the data. Basically, they got a list of faculties all across the universities in US, and then they labeled them with the research area.
Like the same method you've been gathering
Yeah.
the data.
Right.
And in fact, they at some point they opened it up for anyone to look at, so I could go in and change my information
Yes,
there.
yes.
And I went and changed a bunch of information for other Utah faculty that they had wrong. So,
Yeah.
so
You can perhaps not change or just leave a comment.
sorry, leave a comment, and then they very quickly that the person in charge, she changed everything. And
Yes.
so she was, yeah.
Yes. And now it happens that they are, and they are updating the data. So
Yeah.
they have not kept the spreadsheet open now.
Oh really?
Yeah, they are updating the data.
But you have the spreadsheet.
Yeah, I have the spreadsheet copy.
Is your data larger than theirs?
No, I have picked a subset.
Ah,
So
okay.
basically, they have various, the research areas. They have around say 10 or 12. I picked just 6. So what research areas we picked was algorithms and theory, AI, machine learning, hardware and architecture, networks and communication, and databases. So these were the 6 research areas that we picked, and then we picked the faculties who belong to this research area according to that Brown spreadsheet. Okay, so this is how we collected the faculty information, and we have the labels for them also. And the next job was to form the edges. So there was another very tiring job, which was to get the DBLP ID of the faculties, get the DBLP ID of the faculties and get their publications, and then do an intersection between all possible pairs of faculties and then form the edges.
So this was tricky for many reasons. But
Yes, so this was tricky for many reasons. It was in fact very tiring because we had to go ourselves and see what the DBLP ID would be for a faculty. For most of the faculties, we could search the DBLP ID, but for many faculties, this had conflicts. So let me tell you what DBLP ID is. So there is.
can you pull it up? Can you actually show up like a DBLP page?
Yeah. I pick your page in DBLP.
Fine, whatever. Maybe
Let me
shrink it.
show you a little bit. So this is the DBLP site. Basically, it has the information about different publications and who was the author and everyone. So this is Suresh's publication. And if you see the DBLP ID for Suresh, it would be this.
The V also?
Yeah, B also.
Oh, okay.
What does that mean? The V?
Basically, if
First
this is kind of ID by which you can search the DBLP database.
That's the key use. That's the
Why
that's
not
the
just
key,
the
that's
last
the key.
name concatenation with the first name? Sometimes?
It's-
Ask DBLP. That's what they use.
Yeah, okay, no, I thought maybe.
I mean, that's what they use, right? So we can't really.
Personally, I don't think that first name, last name is a good key idea.
Maybe it helps for them to
It's
search.
not adding any information.
So basically, we had to get all these DBLP IDs, and then once we had these IDs.
Well, click on someone's name.
Sorry.
Click on someone's name there.
Someone's name. Neil Patwari.
Yeah, sure, I know. See, P. Neil Patwari. It's all good.
Neil.
And if can you, is there a way to? I just yeah, no, it doesn't matter. It's the same thing. Yeah. No, it's fine.
I'm sorry.
No, it's fine. It's fine.
Okay, so basically you can then get the list of conferences, a list of publications that that person has had, and then do an intersection between all the.
Who's Neil Patwali?
He's a prof here at Utah.
Huh?
He's a prof at Utah.
He's working with Matyaj Gam, Simon Kazina. These are all Slovenians.
Okay.
I know them. I was,
Okay.
done something.
Oh.
Okay. So and then you have to do the intersection between the publications to form the edges and their weights. Okay.
So why do I do if I have to do an intersection? If I look at my page, I just did a list of all the people I worked with, right? Those are the edges, right?
But how do you get the weight of the edges?
Well, oh, I see. Just
Yes.
but for each pair I do a count. You're saying
Yes,
that's
yeah.
okay.
That's fine. Okay. So.
So did you just crawl this data and then build a local graph? Is that what you did? You just crawl this entire set?
Yes.
But you can download the UMP data, right?
Yeah,
In
you can
triple
do that.
format.
You can do that as well.
Yeah.
But then, if you download, you have to write programs to, parse the data.
Yeah, it's in
build-
triple format. It's very easy to parse.
Yeah, it's very easy, but the easier one would be to make the calls. So it has an HTML API which you can call and just get the information. But
I
that's
don't know how
no-
big is the graph, but because I played with DBLP.
Okay.
And Stanford
That's
Stanford
another
has
way
the
definitely.
DBLP published, so it's
Yeah.
you just download the triple data and create a graph.
Yeah, that's another way which you can do it. But I used just the HTML API and I used to query and get the results.
Okay. I mean, there's some APIs you can only query, some APIs where it makes sense to download it, depending on the data set you're working with.
Yes.
Right. For the data sets, for example, that we have on our data page,
Mhm.
those are all downloadable data sets. So you can just download them and play with them locally. For some data sets, you only have, like Twitter, you only have API access
Yes.
to it, right? So you have to then query it.
Yeah. So I started with the API access, so I just went through.
Yeah.
Sure.
Did you write the crawler yourself or is there?
Yeah, myself using Python. So basically, what we have now is the nodes, which are faculties. We have their labels, which is nothing but the research areas on which they work on, and the edges between them, and they are weighted.
So a couple of things I want to point out, right? So every data processing system, right, has a data gathering process, and what you're describing now is data gathering process. One thing you didn't mention was the issue with accents, accented names and stuff. You had a lot of problems with that, right? Remember? With
Yeah.
using Unicode and stuff. I mean, these
Yeah,
seem
I
like
was-
minor
I-
details,
I-
but actually
I-
important, huh?
Yeah, I was kind of skipping that, but yeah.
No, I think
one-
these things are, I mean, they're useful to understand that
Okay.
there's a large process involved in doing this, that you have to clean up this data in some form, right?
So basically, what Suresh is pointing out is when you are.
In fact, look at that name there, Alvarez.
Mm-hmm.
Click on that one.
Actually,
The last name, the Juan Antonio Alvarez. Click on that. Yeah.
yes.
Yeah. So look at the URL now.
Yeah, see. And if they have more than two names, like they have first name, their second name, and third name, and even fourth name, then it's much more problem. So I guess there are a lot of names involved. So here, I think his ID is this.
So you need to deal with the Unicode and convert that in
Yes,
some form.
yes. You have to do it with Unicode. Another major problem is the DBLP. For a very few people, it has duplicate IDs.
Yeah.
So you have to kind of concatenate the publications. You have to first, it's difficult to know the DBLP IDs, and then you have to do the concatenation stuff.
For few people,
Yeah, for few people, they have
duplicate
duplicate
IDs.
Yes.
As in for one person, you have two IDs.
Yes.
Sometimes a
Why is
middle name.
that?
Sometimes someone has
I
a
don't
middle
know.
name. Sometimes they weren't consistent about using the middle name.
Ah.
Sometimes someone got married and changed the name, or they didn't change their name. And,
Yeah.
Like there's a bunch of papers with Monica Rauch Hensinger, Monica Hensinger. They're all the same person, but they have different names for that. And so, and if you don't put the middle initial in, that can be a problem. So,
So there are many such the problems which you face when you are trying to build your own data set. So this was one of the major problems. And once you have this data set, the another problem comes that if your data set becomes too huge, your algorithms might not run very well. In fact, this brings me to the point where we in fact tried to expand this graph. So first we had the graphs only consisting of faculties, and then we had.
so hold on. You said you filtered the Brown 2200 list to the
Yes.
faculty in those 6 areas,
Yes.
and that gave you how many?
Oh, that gave me 809 faculties.
Was it 8 or 909? I thought.
I filtered some.
Okay, so there's 809
Yes.
vertices.
809
Correct?
vertices, yes.
Okay, and then you got some edges between them.
Right.
Do you know how many edges there were? Roughly?
No,
Ballpark.
not. I don't
Okay. All right. So now, carry on.
Okay. Yeah. So basically, the graph that I found had 809 nodes, and then we wanted to expand the graph. I'll tell you why we wanted to expand the graph, and basically we wanted to also involve other people whom these faculties with which we found the graph had papers with. Basically, the students as well. So we again passed their DBLP pages and got all the people with whom they have had publications, and got number of nodes then expanded to almost 45,000 nodes.
So in one hop, just going
Just
one more hop,
Yes.
you went from 809 to 45,000.
Yes.
Yeah.
It was basically too much.
Yeah, because the Brown database not only did not have students, it did not have international people as well,
Yeah,
right? That was another
right,
issue.
right.
We had a lot of international collaborations, you don't have a list. So, and why was it important that you,
Right.
why was it a bad thing that the Brown list didn't have those names? What were we getting from the Brown list that was important?
Which
Okay,
names?
first let me come to the research problem.
Okay, fine.
that is-
Huh?
Which names? Student
Students
names?
or foreigners?
Okay.
Yeah.
Okay. In fact, when I was trying to expand the graph, I want to thank Jan, Meena, and Suresh who helped me trying to expand the graph. And there were other people too who are not here. John.
You can name them too.
Yeah, John, Parasaran. Yeah, these people.
Prashan also did something?
Yeah, Parasaran did.
Doesn't he have work too?
Yeah. So, and I needed help in labeling the conferences so that I could label the notes.
Do people understand the issue we're talking about here? I feel like this has not been very clearly explained. Do people understand what's going on here, why we're having all these problems? Any?
Yeah.
Yes? No? Good. Can you ask a question? Phrase your confusion in the form of a question.
I don't understand what is the question. I mean, I came later.
That,
That's your fault.
that is your fault. But, apart from that. Does everyone else understand why this issue with labeling is coming up?
Okay.
Okay, good. It's fine. Everything seems to.
Everyone seems to understand.
Yeah, except Sharad, but he was late, so it's fine.
Okay.
That's me. Maybe you can briefly
Okay.
explain.
Yeah, let me explain.
Also, Nitin, can
Here.
you give us some
Thanks.
how sparse and how dense was the graph? As in, should we
I'll show you in fact the
Oh.
figure. So
Thank you.
in fact I should bring that up.
Yeah.
Are you going to put your database online?
Oh yes, I'll do
We're
that.
working on it.
It's really valuable.
Yes,
Okay.
I agree.
So this is just consisting of 809 nodes. And right here because
Al is the light blue. It's hard to tell actually.
so Al is somewhere here. You can probably see the biggest community as algorithms. There are smaller communities as well, which you would have to focus to understand. So there is one community
As
here.
databases.
There's one community here. These others here.
It's about machine learning.
May I give a suggestion?
Yes, it is.
Choose colors with more contrast, as in like maybe dark red.
Yeah, I chose,
mean,
but it's not showing up in the presentation.
Really?
Yeah.
Okay.
It
The
somehow
H and
looks
W
different.
and the algorithm, they are very similar in color.
Oh
The
yeah.
algorithm and AI also.
It looks different in the.
The colors here are very different.
Yes.
Okay.
Yeah, like ML is basically orange.
Yeah.
It's a projector problem. Which is not to say we should try to do better colors, but yeah, it's a projector problem.
Nice.
So it's actually we can see the communities in the real world data. Right? Okay, so I'll quickly talk about what problem was it in labeling the data. So when we started with the Brown spreadsheet, we picked the faculties. We knew what their label was. We knew what their research interest was. But when we are trying to expand our graph and also trying to pick the students and other researchers who have had the papers with the faculties, we don't know what their research interests are, right? So this is the labeling problem that we faced, and in order to come up with, the solution was to first label the list of conferences and journals.
So can you maybe say one sentence about why we are obsessing so much about labeling? There's a good reason for it, I think. And
Right.
maybe just once, I know you're going to talk about it later,
Right.
but if you can just give us a sentence as to why we care about this labeling so much right now. Can you just say that, and then you can answer a question? Yeah.
Okay. So this brings Suresh's question brings me to my research work, which is like what we are trying to do is we want to measure how much influence a community has on a node. So given a graph and given a community structure in the graph, what are the possible ways in which we can measure the strength of influence of community on a node?
Okay.
Okay, and if we are trying to solve this problem, we definitely should know. I mean, the prerequisite is to know the community structure,
Right.
and that's
In order to solve this problem, you need to look at the networks through the time, the evolution of networks. You cannot look
I
at
would
the-
replace the word need by could.
it depends what
But
you're
it's,
solving.
you know, the system of influencing and propagation of information is very similar. It's very dynamic system. It's like you're going to mention that it's an iterative system.
Influence and propagation are related, but not the same thing.
But these papers that they have collected is during a portion of a time period of a time,
Right,
right?
right.
So it has the time factor.
If you wanted to use it, if you
have
had-
the time information?
Right.
Well,
You have
yeah.
timestamps.
No, we
It's-
could
it's
use the.
static,
I think your
it's
point
not
is we could
dynamic.
use the information if we wanted to.
Yeah, but do you know the time frame for these collaborations that you have collected?
It's basically so far till I guess September, last year September.
But when did it start?
1 year. You mean 1 year?
Oh, not 1 year. I think
Yeah, this is
it's
what I'm asking.
only
It's a
the
lifetime.
end
Huh?
It's a lifetime collaboration.
time. End time.
Yeah, lifetime collaboration. So
Yeah,
it is
lifetime.
considering the time factor.
Sure, and I agree that since people evolve in their areas over
Right.
time,
Right.
it would be useful to do that. But let us now consider a single snapshot of time, right? Or even a short window of time where you believe affiliations are stable. In that time window, you will have a single graph and you wish to analyze it. So the lower level problem is to even understand the single graph.
Yes.
And then you layer on an evolving methodology on top of that.
But what I'm saying, or rather asking, is that this graph is for the lifetime.
Yes, currently it's for a lifetime.
Okay.
But in some sense, in some sense we don't really care about the graph right now as much as we need some graph that has labels that we can work with. Your points are all valid if you want to sort of now start checking to see the results of our experiments. But in terms of just building the infrastructure to do the experiments, we just need a graph that has reliable labels. And then the rest of it will follow after that, I think.
Can I ask another question?
Yeah, sure.
Just to get at- So, you said that you want to measure the influence of a community on a node.
Right.
Shouldn't it be the reverse, the influence of a node on a community?
Yeah, it can be stated either way.
How can a community influence a node?
A community can influence a node. So basically, if you are in a social network,
As in one research area attracts me to work on that research problem, something like that?
yeah, something like that. Okay, let me give you another example. Say you are in a social network and you are connected to people who have various interests, such as music, right? You are connected to many people who have interest in music. Okay, and then because you are connected to the people who are interested in music, they might influence you to buy a certain music album. So if you are connected to people who are interested in a rock band, maybe you will buy the albums which are rock songs.
So this is not an officially approved claim he's making here, by the way, because I would quibble with this claim.
Okay.
The claim that you can use this to infer, because this is the whole homophily contagion problem.
Right.
That there's a lot of work saying you can't tell the difference between I'm in a community because we share interests,
Mhm.
or I'm in a community because they've convinced me to share their interests.
That's right.
These two things are not easily distinguishable from data. You need proper control experiments. I think maybe another way of saying what we're trying to do is merely understand not at a level of influence, in terms of sociological influence, but more in terms of, if I say this point is in this cluster, how certain am I of the statement? And can I give a more qualitative statement about membership in a cluster? Right? So I'm not making dynamic statements about the system. I'm just making more gentle statements about, I give you a clustering. Can I talk about affinity of a point for a cluster?
Right. And in overall, it makes more sense to measure the reverse, right? The influence of a node on a research area.
Well, that's the problem. When you talk about influence on, you're
No,
talking
it's-
about a
it's
process that's
it's
different. I'm not talking about. I'm talking about a more static setting where you just have I give you a clustering, and I tell you, okay, this point is an algorithm's point. And I wonder, well, you'd label it an algorithm. Is it really an algorithm, or is it kind of on the border? Or if I look at the topology of the clustering, where would I put this point? Right? And we're trying to explore different ways of expressing that uncertainty using the topology of the graph. I think we're getting a little bit further afield here, because I don't think this lecture is not about presenting methods research so much as telling us, trying to understand how we do clustering for a particular example. We can talk about this more offline.
Sure.
Yeah, I think that would be
Where
appropriate.
is the x or y coordinates of the nodes? How can you present those?
Yeah.
Oh, so yeah, I have to talk about the layout, which is ARF spring block layout, which by which the vertices they get an embedding in the two-dimensional.
How?
Right. So this layout was presented by Marcus in around 2007. What this does is it assumes the nodes in a graph are connected. It assumes that the edge is like a spring. So, and the nodes are the endpoints of the spring. So, if the nodes have very high weighted edge between them, that means they are very similar to each other. The spring is, the spring should contract, right? And if the similarity between the two nodes is not that high, then spring should get released. So they try to put the graph in that format, basically the spring layout, and then just leave the graph to acquire a natural shape. And this is one of the variations of spring block layout, which is called as ARF spring block layout. ARF stands for attractive repulsive forces.
So it's a very standard way of doing graph drawing.
Yes.
You just put these springs on things and you just let the energy minimization take over.
Right.
And let it. So this is probably the predominant way of drawing graphs in the plane that people use. So it's a nice visualization trick.
Yes. So
And the idea being that you have lots of edges together, it's going to cluster together. Whereas things that are not, you kind of pull apart. And that's what you're kind of seeing.
okay. Yeah.
How do you measure the influence of a node on a community or community on a node?
Okay, so we have been working with various algorithms.
Okay,
So-
wait. Not now. Yeah, that's not.
Okay,
Yeah.
later, offline.
Yeah.
Yeah, sure.
So it looks like there are some nodes that aren't connected with arcs. Does that just mean that the researcher hasn't collaborated with anyone else at the
Which
university?
Where do you see that?
In this,
So, like-
all the nodes are connected.
No,
Oh, they
you
are
see,
all
you see
connected?
something?
Well, I think I do. Maybe it's just that
There are two
I
close
see.
maybe,
So
but
like
there's
bottom right hand side, it looks like there are two individual.
Bottom right hand.
ones.
Oh yeah, right at the
Yeah.
bottom, above the M, Marcus.
Exactly.
I think
Yeah,
there
those
are-
two
above
things.
The M.
Just above the end, those
Yeah.
two things. They are.
Yeah.
There's probably a
Yeah,
small
yeah.
edge between them, and that's it.
Oh, okay.
Yeah.
Okay.
Yeah.
Is
Probably
it
they are
always,
just they have collaborated with each other. That's it.
Gotcha.
Yeah.
does it always come in a circle shape when you use the spring block layout?
Circle shape, as in yeah. No, if you use ARF's spring block layout, so basically there are
Always
other.
comes in a circle?
Yeah,
The graph?
the ARF one. There
Yeah,
are
okay.
other variants as well, so which won't come in the circle.
Oh.
So in fact, I could show the since you asked, I could show the other layout. Is other layout which didn't work very well for me is this. Sorry,
What is it called?
this is also a variant of spring block,
Mhm.
but it didn't work very well.
Why? What was the difference? Do you know?
I actually didn't.
A different algorithm or a different method?
Yeah, it's a variant of spring block, but a different algorithm.
So different parameters or
Yes.
different. Okay.
It doesn't let a circular formation. That's the difference. So you can see the.
So those are
there
the ones you
varies
probably
to
found, the little
collaborators.
isolated ones. Those are the pairs. Yeah.
Yeah. You can see 5 pairs.
Yeah.
Okay. Now, so if you remember when Suresh talked about the spectral analysis on the graph, basically I wanted to do the same analysis on this graph as well.
Hmm.
Basically try to get the Laplacian for the graph and then try to embed it, in 2-dimensional or 3-dimensional space and see how the graph looks. So what I'm going to do now is work in MATLAB to see how we can work with that. So this was my graph, which was represented in CSV format, and these are the labels for the nodes. As you can see, A is 809 into 809 matrix, and the label is 809 cross.
So you don't need the labels right now if you're doing spectral clustering, though, right? That's just for coloring.
Yeah, that's just the coloring, but I'll need the label in further when I show
Right.
how the DSNE works.
Right. So again, for spectral clustering, our input is a graph, and we have similarities between vertices, and you're encoding the similarities as the weight of that edge.
Right.
Okay.
Okay. So I have already made many functions to get the different matrices in graph. So this is one way in which I construct the Laplacian. So, but what I want to do is, there are two Laplacians which are very famous. One is the combinode. Sorry.
Can I ask a question? Sorry, it was in the middle of your sentence. But so we are using as the weight, you are using the number of collaborations, right? Number of papers
Right.
to. Did you normalize the weights?
Good
or
question.
Not? As in.
No, I did not.
No, you did not. Okay.
Good question. Should you have?
I think this is what
I
he was
think it
going
does
to
not
talk
matter.
about. That there are two Laplacian, right? You are
No.
going-
No, that well,
I think
well
so.
maybe,
Kind of
maybe.
normalize.
So yeah, go on maybe.
But you are kind of with the degree to the minus half, right?
Yeah, I am normalizing. So this Laplacian is the normalized one.
So this will take care of that problem.
Okay.
Okay. So when Suresh gave the lecture on the spectral clustering, I think we used the Laplacian, the combinatorial Laplacian, which is
Yeah,
not
d minus a, right? Yeah.
Yes,
Yeah.
which is d minus a.
Yeah.
The other Laplacian is the normalized one, which is constructed in this form. So basically, LPCN is the d minus a, which is the combinatorial one, and this one is the normalized one. Okay, so this is just a function that I have to do.
So is there a reason to do one versus the other? Is there some intuition about why we choose one?
Oh,
versus
yeah, that's a very nice intuition. Basically, the normalized one, if you know what problem you are going to solve, you decide which Laplacian to use. So the normalized one is very useful if you are doing random walks, and it's very well related to the transition matrix. So let me introduce what transition matrix is, or do you think it will be too much?
No, what was your current plan?
The current plan was just to get the Laplacian.
Then
and
do it,
show
then
the
do
eigen
Then go do that.
decomposition.
Yeah, that's fine.
Okay. So I'll get the Laplacian and
We see if we compute the Laplacian matrix and then normalize it, is it equivalent to use the normalized weight on the graph and
Oh, I
then
don't know.
compute?
What does
the
it mean to normalize a matrix?
What?
What does it mean to normalize? You said if you compute the Laplacian and then normalize it. What does it mean to normalize a matrix?
Normalize the Laplacian.
What does that mean?
Because you have d minus a, you multiply from left and right by a raised to minus half.
By a.
A raised to minus half. Because you want to get Laplacian normalized degree matrix minus I identity. This is exactly what Nitin did in his code.
Did he?
Yeah. show
Because
your
he's just
code.
using d. He's multiplying by d on both sides, by square root of d on both sides. Because the degree matrix is the diagonal matrix, which
So
is the which
you
is
have
the d.
you have only
No.
800 people.
I
Yes.
think
I'm sorry,
You have 800 people.
890.
Think can you show your code once?
Yes.
So this is the degree matrix, right? Not a. So it's d to the minus half L, d to the minus half, not a to the minus half L.
So are you confused about the formula for normalized?
Yeah. Shouldn't you multiply by a raised to minus half?
No, no. You normalize with the
so
degree.
one way it is I minus b inverse of half.
Yeah.
It's half.
Yeah, half.
Half d. The other thing is just this half. And L is the d minus a. And
Okay.
other one is
Yeah, I got it. Sorry.
both are same.
Yeah, confusion.
Okay, So what I was trying to do was do the eigen decomposition of this Laplacian and see what we get. So in MATLAB, you can really do the eigen decomposition as I. And you can give how many eigen values and vectors you want. In this case, let's give 4. And you can specify whether you want the smallest eigen values or the largest eigen values. So if you want smaller ones, you give SM. If you want larger ones, I guess you give LG. So if we trying to embed the graph using Laplacian embedding, we pick the smallest non-zero eigenvalues and the corresponding eigenvectors. For that, give us the Laplacian embedding. Okay. So let's run this and see. So as you can see, the smallest eigenvalue is 0, and these are the other eigenvalues starting from the smallest and increasing as we go further.
Cool.
Okay. And let's so if you want to do the embedding of the graph, you would have to pick a set of eigenvectors and then do the embedding. Okay. I'm not exactly sure how many you should pick. It's mostly based on looking at the eigenvalues. You can pick maybe the elbow method works here again, but
Yeah.
I'm not sure about that, so I'll not.
There's no obvious, so you pick some top k, but we don't really always know what k is.
Yeah, if you have fixed number of dimensions, you can just pick as many eigenvectors.
Correct.
But there's no fixed method.
So in this case, you picked 4.
In this we
Or
pick
3,
4,
I guess.
but,
3
yeah,
really.
but we can work with only 3
Yeah.
because we are not going to use
Yeah.
the smallest eigenvalue. So if let's say we do an embedding using the eigenvector corresponding to this eigenvalue and eigenvector corresponding to this. So what we are going to do is scatter. So this is the second column, and
Okay, so you're saying basically take the second and third elements of the eigenvectors for each point,
right.
treat them as x and y,
Yes.
and plot them.
Right.
Okay.
Oh, it's not showing. Okay, anyways, you get very bad result, which I'll show you. I mean, it's not a bad result as such, but it's not well separated.
Yeah.
Okay. In fact, I was trying with different combinations
Of
and
coordinates?
I also sorry.
Different coordinate.
Yeah, different combinations. As in fact,
Why are we plotting this again?
just to see how the Laplacian embedding looks for this graph. It doesn't look very good, but I just wanted
Because
to
the Laplacian is claiming to give you an embedding. And this embedding is okay, well, what is this embedding? It looks terrible. So what usually happens.
it is at least to convince you that Laplacian embedding might not always give you a very good, good looking embedding. You might have to tweak some.
I mean, it's also good to see it because you want to know if I want to treat these coordinates as valuable to do clustering. If I look at the data, I say, okay, I've got garbage going in. My clustering is not going to give me any useful answer at this point. I shouldn't expect any answer. That's going to be reasonable. So it's a good thing to check ahead of time.
Maybe
Is it
does
always
not-
the case?
No, it's not always. Maybe
Depends
it
on the
would
graph,
look
right?
better.
What property should the graph have to this
Yeah.
one to be a good representation, as in like a good looking one?
Maybe if say if you plant cliques and then they are the edges going on between cliques, basically you have several components,
Yeah.
but those components are not very strongly connected.
And you could try that. You could generate a graph and try this code. You could just try it and see what happens.
In fact, I plan to do that if I had time, but
Because the number of zeros eigenvalues is equal to the number of connected components of
Right.
the graph. So then, yeah, if your graph is not well connected, then it will be a good representation.
Yes,
Yeah,
that's
if
right.
It's not strongly connected.
That's right.
This is kind of strongly connected.
Right, right.
Yeah.
Okay, so
Interesting.
let me pick another
Yeah, so the
dimension.
garbage in, garbage out principle is very important in clustering. Right? If you're doing some kind of feature transformation, which is what you do with Laplacians, you better make sure that the features you're getting are actually meaningful. Otherwise, don't be surprised when your clustering doesn't give you any good answers. So it's a good lesson.
So I'm just picking another dimension. Basically, I pick this eigenvector and this eigenvector. Yeah. The result again doesn't look well separated. But it's okay. You can experiment with different vectors, and maybe it's not good here to pick just 2 or 3. Maybe if you pick a lot more eigenvectors, your data would be really clusterable. Right? So it depends how much you are going to pick. So well, we can also do a k-means using this, but
Not much point, is there?
I'm sorry?
There's not much point. Yeah.
Not much point.
Yeah.
So what I'm going to do now is I'm going to run TSNE on this, and then I'll go on to explain how TSNE works. But before that, I'll see I'll show how the TSNE would generate a visualization for this graph.
So before you explain how it works, can you just tell us what's the input, what's the output to TSNE in
Okay,
this
so
case, in this
TSNE is-
example?
For this example, so basically TSNE is another dimensionality reduction technique,
Yes.
which brings, if you want to bring points in high dimension to a low dimension, you can use that technique. And this technique is very favorable if you just want to visualize your data.
What does it stand for?
T
distributed stochastic neighbors.
Neighborhood embedding or something like that. Neighbors embedding.
Yeah, neighbor embedding. And so, in fact, what it does is you can understand from the name itself, but I'll explain it later. So T distributed has a meaning and stochastic neighbor has a meaning.
Sure.
So let me run TSNE in this thing. So this is the MATLAB version. Okay, first let me create my matrix. So I'll just use, I can use the graph, sorry, I'm getting a little confused here. So A is my adjacency matrix for the graph. And I can, so if I give the label in this TSNE function, it's going to just use that labels to color, and when it shows how the dimensionality reduction is happening.
But it's not going to use it to do the dimension.
No, it's
Okay.
not going to use that.
So it's unsupervised. Yeah.
And then you give the number of dimensions, the target dimension. Wait,
The error is reducing. That's good.
it's working. I should start this from the beginning.
Because it's cool.
Yeah, because it's good. Anyways, let's finish this. So different colors which you can see here are different labels.
What was happening?
Oh, let me show that again. So I'll tell you what is happening exactly when I talk about TSNE. But
So you said it's a dimensionality reduction method,
Yes.
right? You don't. Okay, nothing.
let me show this again.
It's basically doing a bunch of iterations to place the points.
It's doing gradient descent.
Okay.
You apply it on the Bayes matrix, adjacency matrix.
Yeah. So
Yes.
so this is bypassing the spectral approach completely.
And why are you applying a dimension reduction on it?
To see the visualization, to visualize the graph.
The way we use
But the
MBS.
adjacency matrix is n times n.
Yeah.
Oh, I'll show why we can run it on graphs. I'll show why we can run TSNE on high dimension
TSNE
points in
is
Euclidean space, and why we can run it on graph as well. It's because the way the TSNE has been created. Okay.
You are
I should
reducing the
start with
dimension to
TSNE.
2.
I'm
You are
sorry?
reducing the dimension
Yes.
to 2.
Well, I won't say it's reducing. It's embedding.
It's, yeah.
To be very pedantic about this, because you have a graph and you are putting it in two-dimensional space. You're embedding it in 2 dimensions. A dimensional reduction would imply there was a dimensional space to begin with. which would be true for say a Laplacian.
Okay, but for a square matrix, weight matrix, columns and rows are correlated. I mean, they are the same thing. If you are reducing the columns, the dimensions.
No. Who
you
said that?
don't-
Who said we're reducing the dimension of
Who
columns?
said this dimension?
No, I said no. I said we're embedding the graph in a two-dimensional space.
You just said it, but before you were saying it's dimensionality reduction.
No, I forget.
Dimensionality reduction. If you have points in high dimensional Euclidean
You can apply for
space.
that as well. Remember how I talked about MDS and PCA? I said you can think of PCA as the second step of MDS, right? Then in MDS you have a weight matrix. You somehow have to first embed it in some Euclidean space, and then you can do dimensional reduction on it. I'm not sure exactly what TSNE is doing, but if it takes a graph, then presumably it's doing some initial embedding of some form, and then doing dimensional reduction on that.
This is kind of MDS, no?
It's
not.
Yes, it's kind of like an MDS.
Because you are like.
So, I mean, it solves the same problem that MDS is trying to solve, I guess is the way to say this.
And why did you choose TSNE?
Because it's probably the best visualization technique.
Out there currently. It's better than
It's the
MDS.
state of the art.
It's highly nonlinear for one thing. MDS is very linear in some
Yeah.
way. Well, I shouldn't say that, but yeah, it's better.
Who said to use MDS? I mean, there are other methods to use.
Right now, TSNE
But
appears
this
to be a
is
popular
one.
method of choice. So.
Okay.
But yeah, I don't know if there's a good theoretical understanding of what TSNE is doing. There's a paper on this, but it's definitely something worth. I want to know more about actually.
Okay, and then the last question, not too irritating. What kind of feature this embedding has that you said to use that? Is it like locality preserving? Is it
Yeah.
global? Okay, locality.
So if you're familiar with ISOMAP and LLE, it's in that same spirit of things.
Very-
That is looking at local neighborhoods to try to flatten out things to make a nice, well-behaved space. So that's philosophically what it's doing. I think he's going to talk more about that.
Okay, so let me talk first about what PCA does. So as we
So you should check your time.
right. So very quickly about what PCA does, or probably why TSNE is better than PCA. In what sense? So let's say we have points like this. It is I'm not sure if many of you would know what manifolds are, but let's say the points are on a manifold. Basically, the points lie on a low-dimensional space, but they lie on a manifold which itself is a high-dimensional space. Okay, so you can think of this as a globe, right? So globe is a manifold, and there are many cities lying on the globe. So you can consider the globe as the manifold. Okay, so if we consider, imagine these are the points in very high dimension. Okay, and if you see what PCA does is it will consider the distance between 2 points, this and this, as this. Okay, whereas what TSNE does is the distance is this, right? Because if we know our data is lying on a manifold, say your data is lying on a globe, right? And you want to picture all the points that are on the globe onto a two-dimensional thing, right? And say you had North Pole and South Pole here, you wouldn't consider this distance, right? You would consider this distance if you're trying to embed these points on a two-dimensional plane.
Question?
So what happens if you have, say, a single point that's between like the top of the S and the middle point of the S, like right in that space?
In the middle, on the middle of that line.
Like in the middle of the line,
Oh,
yeah, like
yeah.
you just
Yeah.
have single
Point.
like
Oh.
sort of an outlier. Like would that completely mess up the algorithm?
It will be interesting to see how this point will mess up or not. I mean, it will not mess up.
Well,
but
tell them how TSNE works. It'll become clear.
Right, right. So basically,
Just hold that question. It'll become clear in a second.
right, we have an idea like we know that we are not exactly sure, but we know that our data point would lie in a manifold somewhere like this, right? And that's how that's why we are using the TSNE. So TSNE, it stands for T distributed stochastic neighbor, and what it does different from PCA is it tries to take the small distances between the local neighbors and does not give much importance to the far off points. Okay, and whereas PCA gives the importance to even the far off points. So we understood why we have to give the importance to nearby points, and then now we look how TSNE generates the embedding in low dimensional space. So basically what TSNE does is it first tries to calculate the similarity between the points in high dimensional space, which it represents as a joint probability. So basically, if these are your points in high dimensional space, right? You pick this point as you want to measure similarities of other points with this point, and let's call this point as I and another random point as J. Then the similarity between these 2 points is measured as in if you fit a Gaussian kernel with centered at I, then what would be the probability of picking this point J? Basically, we are getting the density estimate for this point J. If there is a Gaussian kernel sitting at I. Okay. So basically, the similarity from I to J is given as the conditional probability of the Gaussian. So basically, which is e to the power xi minus x j norm divided by and well, this gets normalized in the end. So as you can see, this is conditional probability. So basically, it's not the similarity from I to J is not the same as similarity from J to I. So in TSNE, they do a hack to make this similar. Basically, this to get the similarity between 2 points.
You have sigma I square in denominator.
Yeah, but I'll explain about what sigma I square is.
So maybe you should explain it to show why PI conditional J is conditional. It's not symmetric.
No, because we kept the center. Yeah.
Why didn't we keep the center? I mean, the formula is symmetric.
Mm-hmm.
It would be symmetric if the sigma i's would be the same.
Yeah,
Yes.
that's
If
what
they're
I was
different,
Right,
they are
right.
not symmetric.
Yes. So, okay. So sigma I is basically it changes accordingly. I mean, according to what Gaussian center that you have picked. Basically, if there is too much density around a point, and there are too many points around that point, we reduce the sigma I so that there is a term called perplexity, so that we can keep perplexity as constant. Okay, and basically what I mean is we want to pick same number of points with if we pick a Gaussian center.
Is sigma I proportional to the inverse of a degree of a norm?
We're not talking about graphs here.
Okay.
It's inversely proportional or to that density. Basically, if the density around a point is very high, there are a lot of points neighboring the point.
Okay. So
Neighboring the
does it
points, then
translate
it
the degree of a norm in graphs?
It could. You could. You could imagine doing that.
Okay.
So we will reduce the sigma, the
Right.
deviation if it's too dense. Okay. So, and in order to make the distance symmetric, what they do is they do a hack in which they take the similarity as the average of the conditional probabilities. Sorry, this is I. Capital N is the number of points. So this is how they get the similarity. So basically, we have a probability distribution which represents the similarities of points in this high dimensional space. Right? Let's call the probability distribution as P, capital P, right? And we'll denote these similarities with small p. Okay. Now we want to embed all the points in a low dimensional space, and we'll again calculate, basically get the similarity in the low dimensional space, And
So just interject. This explains why there's issue with the outliers. If you have one outlier point in between the two things of the S,
Yep.
this is how you try to filter out.
Right.
So you look at local neighborhoods, and
Right.
of course, if you expand T, then you'll start picking up more stuff.
Mhm.
But then that reflects your belief that the S is not real because you're saying the neighborhood is so big.
Right.
So yeah.
Okay, so let's assume that we have embedded all the points in a low-dimensional space, and again we again build the probability distribution in the low-dimensional space. Let's denote that by Q. Okay, so basically in the low-dimensional space we have similarity between 2 points I and J as Q I J. But this similarity is not given by a Gaussian, but rather it is given by another probability distribution which is called student's T distribution. That's why there is a T in the name, student T distribution.
If I actually knew statistics, this is a good. This is a very well-known distribution. It has some nice properties, but I have no idea what they are because I don't know
Yeah.
statistics.
I'll explain why they use
Okay.
student T distribution. So, and why not they again in the low dimensional embedding, why not they again went with the Gaussian distribution.
Mhm.
So the difference between student T distribution and Gaussian distribution is the tail. So Gaussian distribution have very sharp tails, whereas the student T distribution will have fat tails.
I see.
Okay, and what we want to do is we want to keep the far away in the low dimensional embedding. We would want to keep the points which were far away in the high dimensional space also far away in the low dimensional space. So because the tail is fat, the probability of picking the far away points is also large.
But the reason they picked the student T distribution is because they wanted to estimate the mean and the variance of the point without knowing the variance.
That's one of the reasons that it does not have the variance parameter. But this is the main reason, because this is fat tailed. Okay, so this is about this, and then basically you have two distributions. One, a distribution in high dimensional space, which is P, and it is representing the similarities of points in high dimensional space.
Yeah.
And another probability distribution Q, which represents the similarity of points in low dimensional embedding, which we want, the embedding which we want, right? And now, since we want to find out the low dimensional embedding, we'll have to somehow get an optimization function which would give the low dimensional embedding. So now here comes the question whether in fact Suresh talked about this in the last lecture. How would you measure the similarity between two probability distributions?
The KL.
Yeah, the KL. So they use KL divergence here again, which is say.
I see. So they try to optimize to match the KL divergence between the constructed high dimensional distribution from the data and the desired parametric form of the low dimensional
Right.
distribution. Very good. Okay. So it's an embedding of distribution essentially. That's what they're doing. Instead of an embedding of points, they're an embed distributions. That's their magic. So their magic secret. Okay.
So what they try to do is they try to minimize. Basically, they want to Q to represent P as closely as possible. So that's why they try to minimize the KL divergence from P to Q to get a very good low dimensional embedding. So this is so what we do is the KL divergence between P and Q would be represented as P log Q. Right. So what they do is they try to minimize this over all possible pair of points. Pij, log, Pij, and Qij. Okay. So they try to minimize this function. And there's a reason why they pick the KL divergence. The reason is because they want to give more attention to the neighboring points rather than the far off points. So, and this particular factor here does that. So basically, if in high dimensional points the 2 points were very close to each other, this value would be very large, right? Because it's the probability. And if this probability is large, and basically Pij is large in high dimension, which means the 2 points are very close to each other, you would want those 2 points to be very close to each other in the low dimensional embedding as well. Basically, you want to have Qij small as well. But if you keep Qij large, then you pay penalty because Pij was large. You pay a large penalty.
Pij is the similarity in high dimensional space. Qij
Is a
in low
desired
dimensional
similarity.
space.
Yeah, so Pij is the ground truth, and Qij is what you want.
You can think you can think this as the penalty that you're paying. You want to minimize this function, but you would pay more penalty for the closer points than you would pay for the far off points, because Pij would be larger for the close
Okay,
points.
10 minutes.
Yeah.
But in high dimensional space, points are not that close to each other.
Huh?
I mean,
No, but what do you mean they're not close to each other?
There's a
Sometimes they're
comparison,
close to each
right?
other. But given the data set, you're constructing a Gaussian around the points, right? So you're creating a variance form.
Right, but as the dimension increases,
but you
Pij
change sigma I
decreases.
according to that.
Pij is well, no, sigma will change.
Okay, so sigma.
Right, because you're always making sure you have a fixed number of points in your neighborhood, right? So,
Okay, so this is the main idea how TSNE works, and basically I now want to switch to why we should normalize our data. I'm basically switching off.
so hold on. So you said this is how TSNE works, and you're going to use TSNE to embed the data. Are you going to show us the picture?
Oh, I just.
Oh, you just did the picture. That's right.
Oh,
And then
okay. Now I want to show why we could use TSNE on a graph.
Why not?
Why not? Okay. Basically, in graph we already have the
PIGs.
real neighbors, right? So
Yeah,
it
PIGs.
makes it even easier
Yeah.
to use it on graphs. So that's how I could use that. That's just one setting.
So what is the final clustering that you want to do in the graph, though? I mean, so we're trying to do things like where we say, take the ground truth data on the graph, and then we run some kind of, in other words, where are we using the fact that we have an embedding in what we want?
Oh, I
Yeah.
just use that for visualization purpose.
That's it? So not using it for anything else in the graph?
Don't you apply clustering on the embedding?
Oh, we can do
We
that.
weren't doing that, but you could.
Yeah, we can do that, but since the time is very less, I wanted to switch off to the other topic. But we can basically, you saw the picture when we got the embedding using TSNE of the graph, right? You can run the clustering algorithm, any clustering algorithms, k-means and as such, and you can get some results.
So no one has figured out what would happen if you took, so the spectral clustering method, as I said, is an embedding technique. So you do the embedding, the Laplacian, you run clustering. You could as well do this with TSNE.
Right.
You could use TSNE as an embedding method,
Right.
and then run a clustering algorithm result.
Right.
So it sounds like, I don't know if anyone's actually looked at what the results of this would be.
Oh, do you want me to get the results?
No, I mean, like, theoretically, what can you say about this? I think it's an open question.
Oh,
So instead of using the Laplacian to do the embedding, use TSNE to do the embedding, and then do the clustering and say, what kind of clustering are you getting? So in some sense, spectral, we know now that spectral clustering in some sense is capturing, certain cut properties of the graph, right? And when you do k-means clustering on it. What we don't know is what it means here. It seems like an interesting question. That's a research question.
yeah. So Laplacian embedding, we kind of got our embedding in just one dimension.
No, in this input, but in general, right?
Mhm.
A Laplacian
Okay.
embedding does a certain thing. A TSNE embedding does something completely different.
Yes.
They're both different ways of getting an embedding, after which you do a clustering. So presumably, they're clustering for different things.
Right.
What those things are, I don't know. Yeah.
Alright. So any more questions on TSNE? I'll switch to normalization now. So I'll first tell what normalization does and why would it be important if you are doing clustering and you
So
want
some
to-
of this happened because of the first assignment, right?
Right.
Okay.
So I didn't see anyone of you mention in the assignment that I did normalize the data. You might have done, but I just didn't see that. So I wanted to take this point. So consider a data set where you have a person's age and the salary that person earns, right? And if you try to draw a plot between the age and the salary, so age would be something like this, 10, 20, 30. And if you draw salary without scaling, it would be like, say 1,000, 2,000, something like this, right? This is how it is in Euclidean space. You don't see the scaling happen, right? So if you consider points, it would be and say your company is giving salary say 1,000, either 1,000 or 1,500 or 2,000. You'll see points somewhere like this. So if you apply clustering on this data, what it's going to do is it will just cluster based on your salaries, right? So why it has happened? Because the k-means algorithm, if for example you take the k-means algorithm, it does not do the scaling by itself. And if you take any 2 points, the distance is majorly determined by the salary, not the age component, right? So basically you are giving more importance to the salary rather than the age. Okay, and that's why since you're giving more importance by scaling one of the dimension, when you do the clustering using k-means or something, it would give more preference to this variable or dimension. That's why it will do the clustering based on just this dimension.
And again, that may be what you want, but you should be aware that's what you want.
Right.
You shouldn't just say, oh wow, I got this nice clustering.
Yes.
You should be aware that you've actually changed your distance function in some sense by emphasizing one over the other.
Yes. And yeah, so what point Suresh brings out is maybe you have a set of features of your data, and you know you want to give an importance to certain feature. I mean, you know that if I give more importance to a certain feature, I'll have their data more clusterable. Right? In that sense, you would want to scale that feature. Okay. So to end this, probably I'll just show what's the difference between normalized data and unnormalized data.
But you don't normalize the data, you normalize the Laplacian matrix, right?
I'm sorry, this was not about Laplacian.
What do you mean by normalizing data? You don't normalize the weights of the edge. Edges in your graph.
It's not about graph.
Okay.
It's not about graphs anymore. It's talk about points.
It's just about points.
We change topic.
Just a German one.
I think my laptop went instant. Very good. I'll get this time.
They do that? Why?
What?
Nothing.
So I obtained some code from Stack Exchange, which I'm going to show right now.
This is from Stats? From which Stack Exchange? From Stats.Stack Exchange?
I think it was, I don't remember.
Okay, I'm just kidding.
Okay, so
There are two
this
clustering.
is unnormalized data, right? And let's see what happens with the normalized one.
It was
So,
Yeah.
so I'll just remove the denormalization part and see what happens. Hope you had a good look at the data. So now I'm going to normalize.
A little bit.
Actually, I should show them together. Otherwise, you wouldn't notice the difference.
They look the same to me.
There is a difference.
No, they're closer to their launch spars.
You can see, basically what you can see is the points, they come closer to their centroids.
Ah.
Don't close this and show the other one.
It'll pop. Will it pop a second window if you do it?
Yeah, it did.
They certainly say that it
Just go underneath this window and
say this.
We don't need to close it. You just run the command.
Yeah, don't close this. Just
no, don't click. Don't click.
No, it will not go away.
It won't go. Or
It
Windows.
won't go.
Map.
If it goes away.
Okay, and then you want me to
Too late.
denormalize anything.
Put the window back up. Then. See if you can see it.
Okay,
Now,
yeah. This is the one with normalization.
Okay.
what happened?
You did it. Okay, I see. Go back.
Oh, something. Oh, it plotted in the same.
Oh, that's
Oh, it did.
That's good.
Interesting. That's good. That's good. Yeah. So what? Just okay. So the lines are the normalized data. That's kind of hard to tell, but yeah. Okay.
What is this line?
That's the normalized data got squashed, right? Because the scale changed.
Maybe I'll post the link of Stack Exchange, which explains.
Yeah. By the way, you realize that because it's automatically scaling, it kind of normalized it for you, even in the unnormalized data. So you actually are not seeing different plots because the visualization normalized it for you.
Yeah.
Whereas you want to force it to unnormalize the scale, so you actually see the problem.
Normalize your y-axis.
Well, unnormalize your y-axis, I guess. Anyway, so okay, yeah. Now, I think the point of this, right, and I think the larger point of the lecture itself, I think, is that the way you construct the features to put into your clustering algorithm is often as or more important than the actual clustering algorithm you run. And this is a constant issue with clustering because you are really trusting the features to reveal the internal structure of what you're looking for. And so while in this class we seem to be overly obsessed with algorithms, this in some sense is a mistake because the features are almost as important. Except that there's no nice sort of structured pedagogical way to talk about features. So this lecture was one attempt to sort of expose you to the idea that features are important and there are different ways of extracting features and we should be careful about it. I don't know if I can, it's not easy to put together a systematic way of doing feature exploration. There's just a lot of tricks of the trade. And these are just some of the tricks that we've used and that people tend to use. And visualization is plays a key role in this to sort of see what's happening.
So will the rest of the class focus on representation learning?
No, it will not, because I don't know enough about it to say anything intelligent. What I do want to do is I want to talk about validation. I'm going to spend the next couple of lectures before spring break talking about validation and different ways to do validation of clustering, which is also an important issue. Right? Because if you say, okay, I got a clustering, I want to know how good it is, and for unsupervised problems, that's really a big issue. Because there's no natural way to do validation. You have to have some ground truth, you have to compare, how do you compare? I'm going to spend some time talking about that. And then we're going to get into some of the big data stuff, right? How do you do big data clustering? When you have more than 800 points, for example, and you want to cluster. So no, representation learning is, I think it's still a work in progress, the whole area. I don't think anyone really knows what's going on in representation learning. We don't know, for example, what an autoencoder does, right? We don't know what a ConvNet is really doing when it constructs features. We just know it does something. I don't think it's at the point now where you can teach it. It's one thing to read papers, but I don't know if I can say anything intelligent about it, or anyone can for that matter. So no, we won't be doing representation learning. I might talk about metric learning, which is a related thing, which is a bit more concrete. I'll see how things go. Okay, all right. Well, thanks, Nitin. It was very good.
Thanks for the class.
So since you're working on this DBLP, so a while